Hello, everybody. It's an honor for me to present here our work we have done with PowerDNS and Knot. As already heard, my name is Klaus Darilion. I'm head of operations at nic.at. We are running the .at top-level domain registry. I'm working there as a Linux sysadmin, and I'm from the beginning when we started our RcodeZero project. I was working on it. This is now for more than 13 years. So maybe you wonder now, what is RcodeZero DNS? We are having two products. One is a secondary DNS service for top-level domains. For example, we are hosting ourselves and plenty of other TLDs. But this is not the topic for today. We have also a primary or secondary DNS service for second-level domains, which is targeted for enterprises and for registrars or ISPs which have plenty of domains. So we are running more than 50 nodes globally distributed. We have two independent Anycast clouds, and currently we're hosting more than 4 million zones. What was the reason for this talk today? I will present you the setup we had and the problems we were running into, and why we added Knot and how we do it. Then what were the new problems and how we could solve them or not solve them, and finally some conclusions. So this is mainly the architecture when we started 13 years ago. On the left side you see our central, we call it control servers. We have a main PowerDNS nameserver, which is driven via the PowerDNS API. We have a REST API for our customers and a portal where they can log in and do the zone provisioning, record editing, and so on. Primary zones will be hosted directly on our PowerDNS. Secondary zones will be transferred from the customer's primary name server. We are using PowerDNS with Database Backend and the PostgreSQL database. So that means every domain and every resource record is stored in the Postgres database. So then we used native database replication to replicate the database to our Anycast nodes. So on all of our Anycast nodes, we're running also a Postgres database, the replication slave, and we have a PowerDNS which receives the DNS queries, take a look in the database, and then answers the DNS queries. This is more or less what we started 13 years ago and was running until last year. In this architecture, the replication is really fast and really stable. So the native database replications are really stable. And also PowerDNS is very flexible. As it is database based, we can use like triggers in the database or changing the queries, doing lots of business application in the database, and this is very convenient. But there's one drawback, it's the random subdomain attacks. Because if you have a database backend, every query, which is a random query, is not yet cached in PowerDNS, so we will end up with a database query, and this is the slow part of the whole setup. So that means running PowerDNS with a database backend is too slow for handling high volume random subdomain attacks. So we implemented different workarounds, like putting a DNS dist load balancer in front of it and dynamically moving targeted domains from the PowerDNS backend to an NSD backend. But in the end, it showed it was not fast enough because sometimes those random subdomain attacks are so heavy but so short that it's faster than our detection and our workarounds. And so we decided to having a faster name server for all of our zones. And as Knot has the reputation for being the fastest open source name server available, we just decided to use Knot on Knot. So the engineering requirements were, we want to have Knot as public facing name server. But we keep our provisioning based on PowerDNS because as we said, we have lots of business logic implemented in the database, so we could not swap that out easily. So basically, it drills down to one question: how do we get the zones from PowerDNS into Knot? Somewhere we have to do this. And this question can be separated into two smaller questions. The first thing is the provisioning. So with provisioning, I mean Knot has to know for which zones it should be authoritative or not. So dynamically adding or deleting the zones on Knot. The second part is the zone data itself. This is already answered because there's only one mechanism to get zones out of PowerDNS and into Knot. It's the standard zone transfer. So the question is, how do we do the provisioning on Knot? The first thing we evaluated was dynamic configuration of Knot using the Knot control utility. If you don't know it, it's like similar like with the bind RNDC utility, and you can dynamically add zones by dynamically changing the Knot configuration. You have some kind of, let's say, transactions. You can begin like a configuration transaction with conf begin, with conf set, you can do the configuration, and with conf commit, you can commit it. But we were testing with 1 million zones, and this was very, very slow. So like it took us 1 minute for adding a zone or removing it. And so we decided, no, this is not usable. At that time, also the catalog zone support was rather new in Knot. And I asked the Knot developers if it is ready to handle like a catalog zone with 1 million member zones. And they said, nobody has done that yet, but please do it. We want to have the results. So we decided to do it. So then there's the question, how do we produce the catalog for the Knot? At that time, PowerDNS 4.7 has already support as catalog producer. So we could use PowerDNS as a producer, Knot as a consumer. But PowerDNS does not support outgoing IXFR. So that means if we have 1 million zones in the catalogs, that would mean like every time a zone is deleted or added, which can happen every few seconds, we would have to make a full RXFR of 1 million resource records. And that doesn't sound very nice to us. And my instincts also said that maybe it's too dangerous in the beginning now because catalog features are very new. And for whatever reason, if the consumer produces an empty catalog for whatever reasons, maybe then immediately all the zones are removed also on the secondary name server. So we were looking for another option. And the solution we did was somehow we make an initial dump from the PowerDNS database and writing a standard catalog zone in text zone file format. And Knot loads this catalog zone as a primary zone. So this is the beginning. And then whenever there's a change, like a domain gets added or deleted, we send a DNS update to the catalog zone and using dynamic DNS to add or remove the members. So that means on the architecture changed slightly. On our central controls name servers, nothing changed, only on the Anycast name servers. We put Knot in front of PowerDNS. And we have a small daemon running next to the Postgres database. We're using triggers to get changes in the database. And every time a zone gets added or removed from the database, our tool creates the update message and sends it to Knot. So then Knot will dynamically add or remove these zones. And if necessary, transfers the zone from the local PowerDNS. So when we take a look internally in PowerDNS, it looks like a little bit like this. On the left side, we send the update to the catalog zone. And at this time, Knot is handling this update like, or the catalog zone like a normal zone. The update gets applied and done. Then it looks up or detects this is not a normal zone, but a catalog zone. So the catalog processing application in Knot is triggered. It checks the differences and dynamically creates or deletes the secondary zones, and if necessary, performs the zone transfers. And there we had our first problem. The response to the update was usually quite fast, like 1 second, but the catalog processing took like 30 seconds up to 200 seconds until the member zones were created or deleted. And this was, of course, too slow. So we implemented a workaround by not sending every change in the database as a single update message, but we were batching multiple events from the database into a single update message. So that was much better, but it was still a workaround. And so we were talking with the Knot developers about ideas and how we could improve that, and splitting up maybe in multiple catalogs and so on. And at what time they found like a solution. They did some refactoring of the code, and finally the catalog processing was down to 1 second, sometimes up to 5 seconds. But that's, in my opinion, really fast. And so we said, hooray, it works, we can use it. The second problem we ran into was the zone bootstrapping. When we set up a new Anycast node, of course, the database needs to be replicated from our database master. But then when we have all the zones in the database, we also have to move the zone data from PowerDNS into Knot. And also, depending on the hardware, like those 1 million zone transfers took like 2 to 8 hours. And that's really like slow, because the deployment of a new location was suddenly stuck for 2 up to 8 hours. And the second thing, how do we know that when is the bootstrapping finished? So there is no indication from Knot telling us, so I'm finished with bootstrapping all the zones. So we had to implement some outside monitoring to receive status of Knot and to know when we can put it into production. And regarding the catalog bootstrapping, we implemented a workaround by not bootstrapping all the zones via an AXFR, but preloading the catalog, which is an LMDB database, from another location which is already in sync, and having like deploying already an LMDB database files, and then only syncing the changes since the last preloaded LMDB database. Another problem were the restarts. Knot restart takes, depending on hardware, like 30 up to 300 seconds. With PowerDNS, this was not even 1 second. So we had to change our workflow. We could not even just restart the name server in case of problems or configuration change. Now we have to disable the BGP announcement, restart PowerDNS Knot, and then only then we can enable the BGP announcement again. Another problem are alias records. Alias records, sometimes also called A-name, is a meanwhile deprecated substitute for C-name records at zone apex. PowerDNS supports the alias, and of course we support it also, and our customers use it, but Knot does not support aliases. So we had to find a workaround. The workaround was to periodically retransfer those zones from PowerDNS to Knot, because on every outgoing AXFR, PowerDNS resolves the alias and puts in the correct IP address. So we just make a cron job. Every minute we retransfer all zones periodically. Only the zones which has an alias resource record within. But then we found out some load balancers, which are the target of those alias, have like a TTL of 30 seconds, and customer wants to have those fast detection of alias changes. And we have 11,000 zones with an alias resource record, and retransferring all those zones takes like 150 seconds. So another problem is also that Knot is unresponsive during those massive incoming AXFRs. So alias is still a problem. We're working like we have a plan, but we have not implemented it yet. Another, in our case, in our option, a big problem is zone synchronicity. We do not know if Knot is in sync with PowerDNS. And what does it mean, being in sync? Knot, we mean, has Knot the same zones configured like PowerDNS, And does the zone have all the same serial on both name servers? And in DNS, nobody knows if zones are in sync. The primary just sends notifies, but does not care if a secondary fetches the zones, and also it does not track which secondaries fetch the zone. The secondary receives notify and maybe act on the notifies or during a refresh check when the refresh GTL expires. But if you ask one of those, they don't know if they are in sync. So we had to implement a monitoring outside. And the first idea was, just sending SOAR queries to the PowerDNS and to the Knot for all of the configured zones, and then comparing the serials. But this would be like 1 million queries every minute. This is somehow a self-made random subdomain attack. So we were looking for another option. The alternative was to get a zone list directly from both name servers and compare, like making a diff and compare the lists. With PowerDNS, getting a list with the serial of all zones is quite easy. It's just a select query into the database. With Knot, luckily, there is the Knot control feature zone status, which dumps you all the configured zones and the respective serial. But this takes 10 seconds. This means for 10 seconds, Knot control socket is blocked. And this was causing issues to some other monitoring and provisioning we have running. So we found the kjournalprint utility. This is bypassing Knot completely. It directly reads the configured zones and its serial from the LMDB data files. There we were hit by another thing. LMDB is very sensible about read logs. And if there were stale read logs on the LMDB data files, we had suddenly rapid growing journal sizes until the disk size was full of the servers. Luckily, the developer had an idea what could be wrong, and meanwhile had fixes in place in the latest Knot versions to avoid those problems of stale read logs. So there are some more problems. There are in the slides, but I don't have time to present them all. So what is the conclusion? The first conclusion is PowerDNS and our SQL backend is like a family way. You have a problem, you stop it, you start it within some milliseconds, and you go on. It's very flexible. You can do database tricks, but it's slow. On the other hand, we have Knot, which is the dragster. It is very fast in like queries per second, but for example, a restart of Knot takes time. Just like if you have a real dragster, it takes time to make a second start. The second conclusion is, finally, it works. It's now in production since 10 months. It would not have been possible without the extensive support from the Knot and the PowerDNS developers. So thank you very much, guys. Random subdomain attacks when using Knot are not a problem anymore. The catalog zones was a good idea because it really eases the zone provisioning. But we're still fighting with the monitoring of the zone synchronicity. This is rather CPU intensive. So what for the future? We need to improve our synchronicity monitoring to make it even more lightweight, or maybe also taking a look at or about alternatives. Meanwhile, PowerDNS has always had a fast backend also. It's the LMDB backend, but it didn't have replication. And since a few months, there is the Lightning Stream replication developed by the PowerDNS guys, which would be maybe worth looking at. Or maybe we can just make PowerDNS with the database backend faster. There are some ideas tangling around, like dynamically loading a zone completely from the backend into the PowerDNS cache if there are certain threshold of queries per second for a certain zone, or implement something like aggressive caching in the PowerDNS cache, just to handle the random subdomain attacks much better. So I'm finished with my presentation. If you have any questions, I happily will answer them.
This is Maarten Willink from SIDN. Thank you, Klaus, for giving me or us this insight into RcodeZero. One question about the provisioning of new Anycast nodes. You mentioned that syncing the database, the PowerDNS database, takes a long time. Did you consider using just PG dump and dump the entire database and then restore it on the node? And then you would also know exactly when the database was loaded.
Actually, the problem is not that the Postgres replication we have. This is like depending on the bandwidth of the nodes done in like 10 minutes or 20 minutes. But the problem we have, once we have the data in the Postgres database, so we have the zones in PowerDNS, then we have to make the zone transfers into Knot. And this is the strange thing, that this takes very long. This takes like 20 minutes, 2 hours, no, 20, we never had 20 minutes, like it's a minimum like 2 hours. And actually, we don't know exactly what the bottleneck is. I think it's how outgoing zone transfers are implemented in PowerDNS, but we have not really tried to improve that, because we found a workaround that we don't have to transfer all the zones. We're using a dump from an existing location. So we dump the like the LMDB database files from Knot at some other location, copy it to the new location, and then we have the then we start Knot. So this means like we have like most of the zones are already then on Knot, and it only has to do the transfer of just recently newly provisioned zones.
Okay, it's something similar, but just on another level then.
Yes.
Okay, thank you.
Like dump and restore, yes.
Hello, this is Fenglu Zhang from Tsinghua University. And thank you for your excellent presentation. And I have a question. You mentioned that the PowerDNS is slow for the subdomain attack. Could you please be more specific, introduce more detail about this?
So PowerDNS, the performance of PowerDNS depends on the used backend. With PowerDNS, you can use multiple backends how to store the zone data. You can use, for example, a bind backend where you can load standard bind zone files. You can use a database backend like a Postgres or MySQL, or you can use, for example, the LMDB backend. Using bind backends, PowerDNS is fast. Using the LMDB backend, PowerDNS is also very fast. So the slowness in PowerDNS is only happening if you use a slow backend, because if you have a random, PowerDNS does heavy caching. But if you have random subdomain queries, the cache doesn't help you. So every DNS query finally ends up into the database. And then the database query just takes time. And it cannot be as fast as if it's like answered directly from PowerDNS in the cache. It's a known issue in PowerDNS when using a database backend. We have done plenty of improvements. Like you remember, like 3 or 4 years ago, if it did for every random subdomain query, PowerDNS was doing 4 database queries into the database, checking if there's a wildcard, checking if the zone exists, checking if the subdomain label exists, and so on. We get rid of that, and we boiled it down to only 1 single query per random per DNS query. But if you have like a random subdomain query attack with 1 million queries per second, you would end up with 1 million database queries per second. And this is just too slow to handle on a database.
Okay, thank you very much.
You're welcome.
Yes, thanks, Klaus, very much.